Hello student, I welcome you all in the class of physical chemistry. We have already started the chapter nuclear chemistry. In our previous lecture, I have discussed the application of radioactive isotopes or radioactive phenomenon. The applications are in different steps. First application we have discussed, that is application of radioisotopes as a tracer technique. This tracer technique can be used in the field of chemistry, or it is in the applicable in the chemical applications. And second applications in chemical, to determine the reaction mechanism, to predict the structure of different molecules by using this tracer technique. We have also discussed medical applications to diagnose and treat the thyroiditis. We can say goiter. Then radioisotopes in the location of brain tumor. It is also useful to detect defects in the blood circulation. It is also used to study bone fracture healing mechanism by using this radioisotope tracer technique. Now, in next application, that is radioisotopes in age determination. Now, in this lecture, we will discuss the radioisotopes in the age determination of different samples. Friends, the disintegration rate of radioactive element is defined as and it is not vary with factors such as temperature, pressure and chemical environments, provided that large number of nuclei that elements are present. Therefore, radioactive decay from radioisotope may be considered as radioactive clock. That means this will give us time period of the existence of the substance. That's why we called as radioactive clock created by the nature. So for this age determination, the first radioisotopes that has been used, that is C14 or carbon radioisotopes C14 dating method, or this method we also called as Libby's atomic calendar. So Libby's and his colleagues discover that radioactive carbon is present in the atmosphere, and using these radioisotopes he developed the technique for the determination of the age of different archaeological sample called as C14 dating. He was awarded the Nobel Prize in 1960 for the C14 dating, that means carbon dating, to determine the age of archaeological sample. The ratio of carbon in the form of atmosphere by the reaction of nitrogen with a cosmic rays, that means nitrogen present in atmosphere react with neutron and to form a carbon. This carbon is radioisotopes plus proton. These C14 radioisotopes are highly reactive and it is react with oxygen in the oxidation reaction to form a radioisotopic carbon dioxide, that is C14O2 CO2. Then it is naturally mixed with the stable CO2 in the atmosphere and also dissolve in the natural water. The ratio of radioisotopic C14 O2, that is CO2, radioactive CO2 to stable CO2 is constant over the age equal to the 1.6 into 10 raised to 12. So this ratio will be the constant. We know the plant synthesizes the carbohydrate in presence of sunlight and water vapor by absorbing atmospheric CO2. This carbohydrate takes by the animal and human being in the form of food, due to which a radioisotopic carbon, that is C14, is then part of animal kingdom and part of plant kingdom by the simple photosynthesis and metabolism process. The mass ratio of isotopic carbon to stable carbon is remain constant in living things, and that is 1.6 into 10 raised to 12. When plant and animal disintegrate or disintegration or decay, sorry, when plant and animal is dead and mass ratio does not remain constant because C14 is radioisotope, it started to disintegrate according to law of disintegration. The half-life period of the C14 radioisotope is 5730 years. Thus, it is possible to find out the age of sample for which it remains as a dead. That means the age of sample in terms of half-life period can be determined by the equation. The equation is A is equal to A0 bracket 0.5 bracket raised to T by H, where A is the amount of sample left after time T, A0 is the initial amount of sample, T is the time gone, or we can say age of the sample, and small h is the half life of the period. If we know the half life, initial amount of sample, and the sample at time t, that is a, so we can able to determine the age of the sample, that is value of t, so that we can find out by using this technique. Similar to C14, the radioisotopes of hydrogen we called as tritium, which is also used to determine the age of the sample. So this method is called as tritium dating method. In this method, it is exactly similar to the carbon dating. Tritium is the isotopes of hydrogen We can symbolic form, we can denote it as a T. It has half-life period 12.33 years. It is quite low as compared to carbon. Tritium is continuously formed in the nature by the interaction of fast neutron from cosmic rays with nitrogen present in the atmosphere. The same reaction is there, that nitrogen react with the fast moving neutron, gives stable carbon, and we get the isotopes of proton. Similarly, this reaction also gives the product of, that is, carbon isotope C14 and the proton. Now it is also gives us a stable carbon and then radioisotopic proton. And the tritium is decayed as it gives helium 3 plus beta minus plus a negative charge particle. Tritium emits beta particle with low energy. Liquid scintillation is used to detect this sample. The ratio of concentration of radioisotopic proton to the stable proton in any sample can be used to assign the age of the sample. This method is useful to determine the age of sample only up to the 40 years. Above 40 years, we can use the C14 dating technique to determine the age of sample. But up to 40 year, we can also use this tritium dating method. The tritium combine with hydrogen and then oxidize into the water, that is H2O. This water is called also called as heavy water. So it is radioisotopic water. This water mix through the rains or water vapors, reaches to the large surface of the water, open to the atmospheric like river, lake and sea. The equilibrium ratio of concentration of radioisotopic proton and stable proton in such a open water is approximately equal to the 10 raised to 18 and is constant. When water from a such source open to the atmosphere is stored, the mixing of tritium water is stopped as tritium disintegrate continuously. Hence, the concentration of radioisotopic proton tritium to stable proton is decreases. The activity of tritium in a fresh sample of water per ml and in a given sample of water per ml is determined by using this equation. So this is well-known equation, that is T1 half is equal to 0.693 upon lambda, that is decay constant. If we rearrange the equation, lambda is equal to 0.693 divided by T1 half. So we also know the rate equation of radioisotopic reaction, that is lambda is equal to 2.303 upon T into log of A0 upon A. So rearrange equation, we get T is equal to 2.303 upon lambda into log of A0 upon A. So T is equal to 2.303 upon lambda into log of bracket activity of tritium in a fresh sample of water per ml, then divided by activity of tritium in a given sample stored water in per ml. So this activity we can able to determine from stored water and fresh water. If we substitute the values, so we can able to determine the time, that is time to store the water, or it is the time from this time the water is stored in this store tank. So in this way we can able to determine the age of stored sample, or age of sample, that can be determined by using a radioisotopic proton. So next is a nuclear fusion and nuclear fission as a source of energy. There are two types of reaction. First is nuclear fusion and second is nuclear fission. That means one single nuclei break into the two light nuclei is called as fission, and fusion means two light nuclei combine to form a third big nuclei is called as fusion. So first let us see nuclear fusion as a source of energy. So let us see the what is nuclear fusion. A nuclear reaction that involves combination of light nuclei to form a heavy nucleus is known as fusion. That means two smaller nuclei, light nuclei, combine to form a third heavy nuclei. Atomic nuclei being positively charged, we know, because a nuclei having positively charged proton is present, so overall charge on nuclei also positive, so they repel to each other, making their union is difficult because repulsive forces. The fusion process is found to be exoenergic. So if fusion process is taking place, the energy will be liberated. At very high temperature, the nuclei may have sufficient energy to overcome these repulsive forces and then it fuse. It is for this reason that fusion reaction are also called as thermonuclear reaction. Because of temperature, the two nuclei will be fused and form a third heavy nuclei. So that's why this fusion reaction is due to the temperature or thermal energy. That's why this reaction is called as thermonuclear reactions. The vast amount of energy is given out in this reaction. The reaction also going on the surface of sun. It results a fusion of light nuclei. The fusion reaction continuously going on the surface of sun and stars, in which four hydrogen fuses to form helium nucleus with loss of mass about 0.02871 unit, corresponding to the 26.7 millielectron volt of energy is liberated. Our sun radiates around 3.8 into 10 raised to 10 20 MeV of energy per second. In fact, it is a very large amount of energy, and hence such reaction has become a potential source of nuclear energy. Reaction of light nuclei such as lithium, beryllium, boron, carbon, nitrogen and fluorine are possible but have mean lifetime is very less than 10 raised to 9 year, hence it is ruled out. The energy production with oxygen, neon and magnesium are found to be very low, but the reaction involved between the carbon nitrogen can produce a large amount of energy. The cycle is also called as a carbon nitrogen cycle. It is first proposed by Bethe in 1939. So let us see the sequence of series of radioactive reactions, that is stable carbon react with the proton gives N13 with gamma particle. This N13 radioisotope is disintegrated into the C13 carbon plus positron plus antineutrino. So in third step, this C13 again combine with the proton and it gives N14 nitrogen plus gamma radiation. This N14 nitrogen again combines with the neutron from the cosmic ray is gives oxygen O15 plus gamma particle. In this cycle again this oxygen 15 combine with the proton to gives nitrogen 15 plus positron plus antineutrino. In next step this N15 nitrogen combines with hydrogen, it gives C12 carbon plus helium. So in this cycle helium and gamma particle beta particle is emitted. So the net reaction will be the 4 proton plus gives helium nuclei plus 2 beta particle plus 2 neutrino plus energy. The conversion of 4 proton into the helium nucleus and 2 positron with release of about 30 MeV energy per gram of hydrogen. So in this way the energy is liberated during this fusion reaction, and this energy we can use as a source of energy. So next is fission energy or fission reaction. That means in this reaction a big nuclei is break into the two smaller nuclei which are radioisotopic in nature. Let us see the fission energy. When heavy nuclei irradiate with the energetic particles such as neutron, they break down to produce a nuclei of medium atomic weight that possess a greater stability and higher binding energy. The process of splitting up of heavy nucleus into the two or more less equal half nuclei is called as nuclear fission. Fission is accompanied by mass loss around zero point 0.2 unit and liberated of corresponding amount of energy. The mass loss during the fission reaction is 100 times greater than that observed in other radioactive decay. The magnitude of energy liberated during this fission reaction is enormous. That makes the process special interest from the point of generating atomic energy for practical purposes. The amount of energy corresponding to mass loss can be explained using a typical fission reaction. The fission of the uranium can be occur by the number of ways every time providing different product. Let us see the reaction. Uranium combined with neutron gives molybdenum. That means high energetic neutron collide with the uranium. It gives a two light nuclei, that is molybdenum lanthanide plus 2 neutron plus 7 beta particle, then 7 antineutrino plus xy. So sum of the masses of the reactant, that means the masses of this side reactant, plus that means 235.0.4, that is sum of the masses of the reactant, that is 235.0439 plus, that is mass of neutron 1.0087. So total mass of the reactant is 236.0526, this part, and masses of the product, that is lanthanide 94.9057 plus, sorry, molybdenum, then lanthanide 138.9061, then two number of neutrons 2.0174, and this is massless particle, that is beta particle, it is only charge, then it is antineutrino plus xy. So the loss in mass delta m is equal to, subtract this 236.0526 minus this mass, that means mass of reactant minus mass of product. So this mass loss in the reactant to product is 0.2234 unit. So this delta m is multiplied by 931, we get the fission energy. The energy liberated during this fission reaction, uranium fission reaction, is 207.9854, or approximately it is 208 MeV of energy is liberated during this fission reaction. So here we stop the lecture. In next lecture we will see the sum of nuclear reactors present in the India. Thank you.